Lecture 19, Input-Output Devices and Drivers. Although the computer's name and typical use, particularly in a course where we want you to focus on something computationally intensive, suggests the main purpose of the computer is to compute, I think realistically we know that input and output is just as important to the usefulness of the computer. I've mentioned already this idea of a computer that takes no inputs and produces no outputs is not only not very useful, but like, how do you know it did anything at all? Right? You know, Schrodinger's computer, is it alive or dead? Does it do anything? Did the program actually run if it had no observable characteristics? So what would you say you do here, Bob? Okay, the thing is about I/O, right? And for many use cases, the I/O is actually the most important part, right? The thing that we want to do, we need to see what we're doing, hear the text that's being read aloud, whatever it is. This is important. But I/O is a messy business, right? There's a very small number of CPU types that your typical desktop operating system might run on. There's ARM architectures, and there's the x86 architectures, and even within those, there's a certain level of compatibility between them. Intel and AMD processors can execute the same binary code, the same x86 instructions. So it's not really that different, right? What we have to do doesn't matter. Like the compiler can just generate the same binary code, and you can ship that same binary, and it'll run on whatever Intel or AMD x86 compatible CPU, or even like an Apple Silicon that has some x86 emulation mode to support it. Okay. The thing is about I/O devices is there are uncountably many in the world, and they are all different. What do I mean by different? Well, keyboards, hard drives, printers, headsets, they're all I/O devices, but they serve very different purposes. They work in very different ways, right? The keyboard is an input device. You use it to type whatever it is you are typing, and that's primarily its purpose. But you can't say that it's only input, right? Because a lot of keyboards, there's a light that lights up when you have caps lock on, so it's telling you something about the state of the system, which does actually suggest that there is some output on it. But then there are other things, hard drives. These are again, for reading and writing data. We've talked about that quite a lot, so there's no reason to belabor that point again. A printer, again, an output device if the printer feels like working today. Headsets could be both input and output if it has a microphone, so you use it to listen to the lecture, but also to trash talk the other team when you play a game. It's whatever it's for, right? It's an input or an output device. So they're all different, right? They behave in different ways. They work on different data. They don't use the same idioms, if you will. They don't use like the same way of seeing the world. So, okay, what are we to do about it? Well, let's take a look at just some of the dramatic differences in speed between the various devices of a typical device. So gigabit Ethernet shows here it's 10 to the power of 9 bits per second. Graphics display, I'm sure, has surpassed this by now. This diagram is already about 5 years out of date, so it's going to be even better now than it was then, and that's fine. Can't argue with that. But you can kind of get an idea. Hard drive is up there. Again, it may have improved a little bit, and certainly with SSDs it will be better. Ethernet, like regular 100 megabit Ethernet, optical disk, reading a CD for some reason, scanners, printers, floppy disk drives if you care about such ancient things, modem. But then down at the bottom we have like mouse and keyboard, and even if you're really good at typing and you type really fast, the amount of data that you can enter with the keyboard is pretty small, all considered, right? There's no no magic that would make typing just as fast as gigabit Ethernet. Like the physical keyboard just couldn't do it. And you might say, well, USB exists, so that makes it easier, right? I mean, it does, but it doesn't, right? USB manages how the device connects to the computer, universal serial bus, and managing the actual device itself is still very complicated, right? You can, and probably do, have USB headphones, USB printer, USB disk drive, and USB keyboard, all of those things. In fact, sometimes it's the only way to connect things these days, unless you use like a wireless headset or wireless keyboard or something like that. But USB is pretty bog standard for connecting just about any device right now. But it doesn't take away the underlying complexity of managing the actual hardware. And we're going to talk about disk I/O in some more detail in a bit. That's actually the next upcoming topic. But for the moment, we want to talk about I/O in general. And why are we going to talk about I/O in general? Well, it's kind of like a lead-in to talking about managing I/O devices, which is a big part of the work of the operating system. Now, the thing is we're not going to talk about the specifics of the hardware, although it might be helpful to review that information if you've taken a previous course on this. So we're not going to be concerned about exactly what signal gets sent over the bus and how to arbitrate between which things get to access the bus and at which time. Like, those things are important, they do exist, they do matter, but they're hardware implementation, and they're just out of scope for what we can talk about in the operating system, because, well, yeah, we only have so much time, and we're getting close at this point already to the end of the course. So, onwards. For I/O, the key parts are the bus and the controller. Okay, we know that already. This is not new. This is not exciting. It is, well, just the physical hardware that makes things connect, the bus, and the controller, which manages the actual arbitration of who gets to use the bus when. Now, hopefully, a significant fraction of this is review, but I think it's worth spending a few minutes to talk about, just to make sure there's no possibility of confusion. But there are three ways that we could realistically communicate with a hardware device, and they are polling, interrupts, and DMA, DMA being direct memory access. This is not a hardware course, but I figure it's worth spending the time on. It's fair to say that not all of these things are equally good options in terms of efficiency, where efficiency is measured in terms of like making best use of the CPU time, right? Things are going to be sort of more complicated. An I/O port represents a connection, how the hardware is connected to the actual rest of the system. And it may typically have about 4 registers. There is a data input register, input, data output register, output, status register, and control register. And the control register is the location to which data is written to give instructions to the device, telling it, please do this thing. And we can check the status of it by, or find the current state of the device by looking in the status register. Nothing here is very exciting. It's not anything that should be new or weird, but it does bear mentioning. And the literature tends to refer to the main system as the host, because the code that's interacting with the device could be the operating system, or it could be user-level code, depending on the situation, so we use the word host. Now, polling is the most basic way to interact, and it's to some extent our last choice, but maybe our only choice. And when a command is issued, then the controller uses a bit to mark the device as busy during the time that the operation is taking place. And when the operation is done, this bit is cleared. After that, the operating system can take the next action, whether that's reading the data or scheduling the next write or just moving on to the next thing. Whatever operation is in progress has completed when we see that that bit is cleared, and then we're ready to go. Now, first thought would be to change the logic a bit so that instead of type polling, the host checks periodically rather than immediately. But Right? It does decrease the wasted CPU cycles, but there is a risk that the data is lost because we don't respond in time. Right? How might that happen? Right? If the storage for the device is very limited, if the data that's currently ready is not retrieved fast enough, then it's possible the data that's there gets overwritten by the next chunk of data before we get a chance to get to it. So, yeah, sometimes, even though we don't always like tight polling, sometimes it might be the best way to ensure that we don't miss any data. And that's, a trade-off. All right, option 2, interrupts. So interrupts we've covered extensively. We've spent more time talking about it really than anything else. It's just based on the idea that there exists some sort of interrupt line. This interrupt request line is hardware, and when the CPU identifies that a signal has been sent on this interrupt request line, it indicates that something is going on and something needs to happen. So the interrupt handler will be triggered. The interrupt handler will then begin executing, and it will do whatever else it needs to do, and at the end it clears the interrupt signal. This description is fully correct, but it's not the whole truth, right? It ignores the complexities around things like, well, what if you want to give priority to certain interrupts? Incoming phone calls are not as important as fire alarms. What if interrupts are disabled? We talked about disabling interrupts very early on in the course. What do we do, right? Interrupt approach does help us to deal with the problem of not responding in time to the availability of data, rather than making sure that we have to check frequently just in case. Interrupts tell us when there is something to do, but it doesn't mean that an interrupt has to be processed immediately. It might actually be preferable to delay handling it until enough data has arrived. But as long as the data is in memory somewhere, it probably doesn't get overwritten unexpectedly. DMA is based on this, make it so number one kind of approach. The idea that it's preferable to hand off some work from the CPU to the DMA controller. The DMA controller is the delegate, and it's responsible for carrying out the thing that has been asked. And DMA is given instructions about what to do. It's a read or a write, a source, a destination, and how much data is to be transferred. And so if we're copying data from USB drive to hard drive, this is great because we don't have to send every byte from the USB drive to the CPU and then from the CPU to the hard drive. We can just coordinate it so it goes directly from one to the other. When the I/O operation is completed, the CPU is still notified via an interrupt, and that does happen. And one thing that may not be obvious from the DMA approach is that the DMA controller isn't totally independent of the CPU, and it can in fact slow down the CPU a little bit because there's like bus contention and it can make the CPU wait, but certainly this is less of a hassle for the CPU than it would be if it were a strictly interrupt-based system. So ideally, a general purpose operating system has the ability to accept new devices being added without needing to edit, reinstall, recompile the code, right? And this wasn't always the case, and it used to be you needed a new compiled version of the operating system anytime you wanted to support some new devices, but yeah, we're past that now, so that's good. And your experience with object-oriented programming or something to that effect gives some familiarity with the solution of how we should accomplish the goal, which is we want to abstract away the details of the hardware and have a uniform interface for interacting with any hardware, whatever it is. Wasn't always the case, right? In the very early days of operating systems, the hardware that the system shipped with was integrated, and the software supported exactly that, and that was all it was ever going to support. When you bought them, you got them as a package, and that was not something you could change. If a vendor did come out with a new module, for example, and all right, we've given in to overwhelming demand and we've decided to support a printer, they would ship a new operating system update, and ship in this case literally means like send you physical media to introduce support for that device. This got to be fairly unmanageable over time because there's too many different kinds of I/O devices, and one of the big successes of the IBM PC is that, well, anybody could create hardware and attach it via a standard interface. So having something that other people can build attachments for is great, right? Do I buy the Hewlett-Packard computer that only supports Hewlett-Packard printers, or do I buy the IBM PC that supports Hewlett-Packard printers and Brother printers and any other printer brand? Obvious choice, right? Unless you have some other reasons outside of this that I'm unaware of, it definitely makes sense that you would want to choose the printer and the operating system that work together. And if the IBM one gives you more options, you're probably going to take it. Save money. Okay, but the converse of that is, well, somebody has to implement support for that device. And relying on IBM to do it was kind of not going to work, because how should IBM know how a printer made by Brother works, right? Why would they? They're not going to buy one and take it home and disassemble it and figure it out. That seems silly. And same thing, again, why should Microsoft know this? I mean, they do sometimes do this, but it's not always reliable. Why should they know, again, the internals of the hardware? And yeah, you don't want to see the USB device not recognized screen or pop-up. Means Windows was unable to figure out what you wanted or what that device is supposed to be. So operating system developers thought that they were very clever. They said, we can shift the work to the hardware developers of implementing the actual support that is necessary for the hardware to work in their operating system through a concept called device drivers. And as the critical drinker would say, nah, it'll be fine. As you will imagine, this didn't go exactly how they hoped. The device driver plugs into the operating system using a standard interface, which is good. That is what we would expect. And we are hoping then that using the standard interface, the operating system and the device can interact without really the operating system implementers having to know a lot about the details of the device in general. It tells the operating system, in the sentence being the device driver, tells the operating system a bit about what kind of device it is, and it will translate some commands, whatever you give it, from the operating system's version to the actual specifics for the hardware. So whatever's going to go out over the bus, that actually is translated by the device driver. Here's the problem. Hardware developers often made extremely poor drivers, right? This is where the scheme falls down. And it's hard to say whether this is because, well, hardware people just didn't have the expertise that they needed to make the software drivers correctly, or whether it's like they just didn't care. Once they've bought the printer, we've already got their money. It's not entirely obvious why drivers were always, or maybe not always, but frequently so bad. The problem was exacerbated by a Windows design decision, and that was to make it so that device drivers run in the system at the same protection level as the operating system's kernel. That means, it is running with maximum privileges, can do absolutely anything and everything if it wants. Some other operating systems have user-level drivers. I can recall installing a user-level driver in Linux to be able to read an NTFS drive at some point. So the concept does exist. Other operating systems also have an intermediate level between user space and the kernel that says, all right, we trust you, but not completely. But why is it bad for these to be at kernel level? Well, yes, a driver, if it's unhappy with the state of the world, can invoke a function that causes the following screen, colloquially referred to as the blue screen of death. Or BSOD, as sometimes called. And the blue screen of death has had numerous different versions over the years. The exact text that you see changes, and sometimes it's a different color blue. But suffice it to say, when you see this, it is not a good day. Now, Microsoft, rightly or wrongly, received a lot of blame for the blue screen of death problem. And I think it's kind of understandable. I think you can probably see why, right? Microsoft didn't make the device driver that caused the blue screen of death, but the typical user doesn't know that, right? They don't understand that actually, it's their crummy wireless Wi-Fi card that they've plugged into the system that's actually the cause. They just know, like, oh, when I try to use Windows, it shows me the blue screen of death, and then I lose part of the document that I was working on. So whose fault it is, if you want to assign fault, yeah, it's not always obvious, but you can see why Microsoft got some of the blame, but you can also see how it's also sort of not their fault. So they took two approaches to remedy this problem, and the first one was the idea of writing and including in Windows a lot more device drivers by default. In fact, for a lot of things, if you just plug in your device, Windows will say, yes, I know what it is, and you're ready to go. Now, the device manufacturer might wish for you to actually add some software that they supply with it, but you might not always want to do that because, well, sometimes that extra software that they add kind of adds nothing except stupid ads to your screen. So if you don't need it, you don't use it. But sometimes it's not present. And when it isn't present, that is, Windows doesn't have a device driver for it, you do have to use the one that's supplied by the vendor. But there's now a much more rigorous test to actually get approval to put this little Windows compatible sticker on your box. And this is a static driver verifier. Static in this sense means that it evaluates at compile time or build time, as opposed to dynamic, which would say at runtime, the performance of the driver. And when I say performance, I don't mean like, is it fast enough? I mean like, is it going to do what it's supposed to do? Does it pass all the tests? Does it ever get into a state where it's going to invoke the blue screen of death, no matter what input you give it? And passing this test gives you the approval to put the sticker on your box that says, aha, this works with Windows 7, 8, 10, 11. I guess you could be watching this recording in the far future, so it could be like Windows 217 at this point. But yeah, it is a step. And certainly this has reduced greatly the amount of times that the average user sees the blue screen of death, or its modern equivalent in a Windows system. But the battle rages on about who is responsible for writing the drivers. Like, who's best placed to do it? Is it Microsoft? They're the ones who know the most about the operating system, and they're software experts. I mean, that's kind of what they do. Or is it the device driver manufacturers? The device manufacturers to write the driver because, well, they are the ones who know the most about the hardware that they're working on. There aren't any easy answers in this regard, and that can be a little bit frustrating, but what are we to do about it? So, with this little digression aside, device drivers, when they exist, connect into the kernel I/O subsystem to mediate between the kernel's I/O subsystem and the hardware device controller itself. And so what we see in software here is shown in blue in the large rectangle above, and then there are the hardware here shown in gray. And basically the idea is the driver is the level in between the kernel I/O and the actual device controller, such that when the kernel wants to issue a command, it can just call into the I/O subsystem and say, do this thing for me, please. And then the I/O subsystem will find the correct driver and pass that along, and the driver can then turn that into something that the hardware device can actually understand once it goes out over the bus. Sounds good. So abstracting away the details of the hardware does make the job of the operating system developer easier, right? Because it does give us a standard interface. It does give us something to work with, and we don't have to have a whole bunch of common code that is repeated everywhere just to account for tiny differences in the various devices. So, okay. Part of the difficulty is that devices can vary on numerous dimensions, right? It is not always so easy to just classify, say, a particular device because, well, they have different properties, so to speak. And here are a few of the dimensions on which particular devices could vary from one another, just to give you kind of a flavor of how much of a headache this can be. So data transfer mode. This is about whether it's a block device or a character device. So a keyboard is a character device. You press A and it sends in the character, letter A. That doesn't mean you are unable to submit more than one thing at a time. Like when you do copy and paste, right? You're doing Control C and Control V, and in the language of user interaction, that's referred to as a chord, like a musical chord where you're playing like several notes concurrently. That still counts as character level device because we're moving around a little piece of data. Whereas if we're thinking about a block device, a disk, we've talked about that, operating on a larger chunk of data, we potentially receive a few bytes or a few kilobytes at a time, and that makes it a block device as opposed to a character device. Second one is access method. So a device may allow only sequential access, such as reading only the next element or next piece of data, or it could allow random access. So when we read data over the network, we get whatever data is supplied in whatever order. It comes to us how it arrived. This is also applying to other ancient devices, tapes. Tape drives are usually sequential, but you can actually skip over them now that I think about it, so never mind, not tapes. But it could be allow random access, right? Reading to or writing from any point. So a hard drive is a random access device. A tape, in principle, is a random access device because you can just scroll around in it if for some reason you had a tape. Any of these devices where you can choose an arbitrary location will be random access. Transfer schedule. So transfer schedule may be synchronous or asynchronous, briefly speaking. And synchronous means that data is transferred with predictable response times. So if we want to read from disk, that's going to be a predictable thing. Now, it's not predictable doesn't mean it's exactly the same every single time, because if we're needing to hunt around on the disk to find the thing that we're looking for, it takes longer than if it's close by. That's fine, but it's still predictable. We have a known upper bound as to how long it's going to take, and we have performance characteristics where we can predict how long it takes to do a read. Asynchronous ones are unpredictable. Awaiting a response that comes over the network, it arrives when it arrives. Network transfer times are kind of unpredictable, just depending on the route that the thing took and network congestion and all of that. Anytime we're waiting for a user, similarly unpredictable. Users behave in arbitrary ways, and they might not answer the yes/no prompt instantly. They might take a few minutes, a few seconds, who knows. Dedication. So a device might be shareable. And dedication in this sense is not about how hardworking it is, but whether it is uniquely assigned to one thing at a time. And so a device that is shareable is something like the speakers. You can play music from the speakers, and at the same time, when you get an email, you get the little notification noise for the email, and it just plays on top of the music without interrupting it. And that works, right? It's not a dedicated device. It can be used by more than one thing at a time. Whereas other things like a printer are dedicated. If we are printing something, we are printing only that thing right now. We can't pause the print in the middle of the page and then print the next thing and resume printing. It doesn't really work. You can't really share it. Device speed. Well, you saw a diagram already about the differences in device speed, so that's a lot. And then we don't have to focus on that really. And then there's transfer direction. And some devices are input only. A lot of the ones we work with on our computer are bidirectional, even in the smallest way. Like I say, if you have the light on the keyboard that indicates whether caps lock is on, that's a software state, not a hardware thing. And so you are actually seeing some output there. But for the most part, there do exist some input-only devices. If you have a temperature sensor, for example, that's an input-only device. And you have output-only device, speakers. They're only used for output, playing your music, or listening to the lecture. And you have many devices that are capable of both. You have hard drive is a bidirectional input-output device. Network is bidirectional. All of those things are, like I say, very common. Okay, so all of those are sort of important distinctions between different kinds of device. And as much as possible, the details should be kept away from the operating system, right? It shouldn't have to know exactly what this is or what that is, or whether or not it's a dedicated device. May matter, it may not. But devices are typically grouped into a few categories so that appropriate system calls for that kind of device can be issued. And when I say appropriate system calls, I mean what we're really talking about is this idea of like whether it's a block or a character device, sort of most importantly, right? If a device is block-oriented, the operating system should be issuing block read and write commands, not trying to get one character at a time. And operating systems are built, if you will, with this idea that we might not be able to predict or imagine or foresee everything. And for that reason, there is an escape call. And the escape call is used effectively to send a command to a device that we didn't think of and we didn't have a system call for it already created. This, like I say, is just sort of recognizing that we don't always know what there's going to be, and so read and write might make sense for certain kinds of devices, but if you need to tell it to, I don't know, change state some other way, that might also be predictable, but it's not always clear what devices can and can't do, so we need to leave the option open for something that, as an operating system, we haven't thought of. And in Unix, this is called IO control, IOCTL. And this takes 3 parameters. And the parameters are a file descriptor indicating which hardware device we're talking about. Remember, in Unix, everything is a file. So, of course, it is a file descriptor. What else would it be? The command number, and the command number is just an integer, which says, execute order 66. And then a pointer to an arbitrary data structure that has the control information and data, and that is whatever the driver needs, right? There's no restrictions on that, because the driver has to understand, okay, execute order 66 means this, and it has the following associated data structure. There's no possibility the operating system can predict this, so it's just an arbitrary pointer. We'll also talk a little bit about block and character I/O. So the block device interface exists, and it's used for block devices such as hard drives, and any such device supports read and write commands, and if it does allow random access, then there's a seek command to jump to a specific block. And we've talked about those somewhat in the concept of working with a file. Right? We want to read from part of a file, we want to write to part of a file, and we might want to seek around inside that file. Same thing with the hardware device. It's just now we're looking at different chunks of the device. We're not quite so much focused on an individual file. And an application typically accesses the hard drive through the file system. Right? We don't usually allow a lot of direct access to the hard drive stuff itself. And so, an operating system can work on a hard drive using these commands, just as an example, without having to care very much about how the actual instruction is transmitted to the physical underlying hardware. Like, why should you need to know that? So we can abstract things a little bit further from the perspective of the developer by using memory mapped files. If you remember this from the inter-process communication topic, then now we're just on the other side of it. And when we're on this side of it, right, we don't have to actually do quite as much, right? Rather than using the block-oriented operations directly, the application reads and writes to and from quotation marks memory, and in the implementation, really that's just some behind-the-scenes coordination to make sure that when the data is written to a particular location in memory, we just flush it out to disk as is appropriate for the request that we've been asked to handle. So that's nice. Whereas a character-oriented device, as I say, resembles a keyboard, and I mean, it doesn't have to be exactly a keyboard because it could be any other character-oriented device, and it operates rather than on read and write kind of semantics on get and put. And get and put are just ways of saying, get the next thing or put the next character. And in any application, you probably don't work with get and put directly if you can help it. There's just so much overhead from doing that, right? So libraries and tools and stuff allow you to build on this to work on, say, a whole line at a time. If you want anything other than terrible performance, maybe you need a buffer for that. Just thinking about Java, right? The default streams in Java are one character at a time, but the performance of those is terrible unless you use a buffered version, just because of the nature of how get and put individual characters would actually work. But buffers are actually kind of nice, and we'll talk about them in a little bit. But the idea of character-oriented devices makes a lot of sense for things that are sort of one character at a time, or at least linear stream of bytes. When we send data to a printer, we are in a way sending a linear stream of bytes to the printer, saying, here's some data, please print it, and it's up to the printer to figure out how to actually turn that into something you can do something with. But like I said, regardless of block or character-oriented, a operating system device would actually be benefiting from, buffering. Why? Well, buffer is just an area of memory that stores the data being transferred either from memory to a device, from device to memory, or from one device to another. So why does that help? Well, one important reason is that it's a good way to deal with a speed mismatch between devices, right? Users type very slowly from the perspective of the computer, and if our intention is to take this data and eventually sort of write it out to disk, it's frustrating and annoying and quite inefficient to ask the block-oriented device to update itself every time the user enters one single character. It's just not efficient. So what we actually prefer is this idea of, we let the user write the data in, it goes into a buffer, and from the buffer, then we'll write it out when we've reached a certain threshold, i.e. when there's enough data available, then it makes sense to actually write that data out. Before that, like I say, we're just kind of wasting our time. Now, if a write is not instantaneous, where does the user input go while we're writing the data out to disk? The answer is, and probably should be, double buffering, which is two buffers. Why not both? While one buffer is being emptied, another buffer is receiving any incoming keystrokes, and this is actually a good way to decouple producing and consuming of data. It allows us to sort of much more easily operate our producer and consumers, even if they have dramatic speed differences. And similarly, it lets people work together even if they need exclusive access to a buffer. While one is being drained, the other is being filled. In the producer-consumer problem that we talked about in this course, we didn't need that. We can operate the producer and consumer on a shared buffer concurrently. But if for some reason you had some scenario in which you needed exclusive access to the buffer to operate on it, well, using two buffers would allow us to continue producing and consuming even when that exclusive access is actually needed. And then network devices. Okay. We know about this. Network devices are fundamentally different from devices that are directly attached to the system, just because, well, there's no way of ignoring the fact that a particular device is not always reachable at unpredictable times, those kinds of things. So the read, write, and seek routines are not really appropriate, and we know about sockets. We've talked about sockets in some detail, and you've hopefully gained some experience in how they work. But that model is also used in Windows. I mean, it's not identical because, sockets are kind of a Unix concept, and implementing them in Windows makes them have their own, shall we say, Windows flavor. But with that said, we don't need to rehash the concept of sockets too badly here, because I think we have an idea about how they work. And we didn't cover it in this course, but it should be in a concurrency course that you take. The idea that the socket interface has a function select, there's also poll and epoll and other similar things that allow you to manage a group of sockets and sort of work with them sort of asynchronously. And invoking select correctly, as annoying and frustrating as it is, allows for some asynchronous I/O. That is, because select returns information about, say, which sockets have data available and which ones don't, we don't get blocked and we don't have busy waiting behavior by trying to receive data on a socket that has no data to receive right now. Right, and it does eliminate some headaches where delays are unpredictable, and delays are unfortunately always unpredictable when we're talking about the network. And we'll also talk about spooling and reservations, because they kind of go together. A spool is a buffer for a device like a printer that can serve, say, only one job at a time. Unlike disk, where it could do a read for process P1 right now and then a write for P2 immediately following, the printer needs to finish the whole job before it starts on the next one. Printing is just a super obvious example of this, but it's by no means the only one. And so what the operating system does is it centralizes the operation of the printer. When you submit a print job, like the print job doesn't go directly to the printer, it goes to the spooling service. The spooling service is responsible for taking all of these jobs and putting them in order, and then dispatching those jobs to the printer when they get to the front of the queue. And then there's the last thing to talk about on this subject, which is I/O protection. Recall from earlier, we've discussed in some detail the idea of user mode and kernel mode instructions, and I think you remember why this is important. So I don't think we need to belabor the point of talking about that again. With that said, we want all user I/O accesses to be mediated through the operating system so that the user can check if that is a valid request. Right? We don't want users to accidentally send incorrect commands to hardware devices. And for some hardware devices, we're not that worried, but for others, if we send, rogue commands to air conditioning system, right? We might end up doing what is called short cycling it, which is it runs for a very short period of time before switching off again. That turns out to be bad for your air conditioner if that happens. So you want to install some safeguards that prevent those kinds of bad behaviors from happening, even if they are unintentional. So it does also provide us some security, and it does help avoid bad behavior that I've talked about earlier, where, say, a user who wants their request to get done faster decides they're going to cancel the request of somebody else. Does it work? It's evil but effective. Unless, of course, everybody does it, and then nobody's print job can ever succeed because every print job is being canceled by somebody else. So that's our typical trade-off. We are getting increased safety, and our cost is reduced performance. However, for performance reasons, we sometimes allow direct access. And this isn't for everything, and you don't always want to do it, but you can if there is a scenario where it makes sense. In the case of a game, for example, it might actually be sensible to allow the executing code of the game to operate directly on the graphics card memory, in spite of the fact that the graphics card is, legally speaking, an I/O device. Why would we do that, and why does it matter? Well, performance, right? If every access to the memory of the graphics card involved going through the kernel, it would result in unacceptably poor performance, which is to say the other team would totally call us noobs. We're here to win, and it would just be too slow. So to make this happen, an operating system can and will basically allow the rules to be broken a little bit. A section of graphics memory corresponding to the window that is your game, and this may be a full screen game, which obviously would make it a little easier for the graphics card, but that whole thing is locked by the kernel to be accessible by the game's process directly as if it's its own memory, without having to mediate through the operating system. Okay, and as we can see, just to close out this topic about kernel internal stuff. Actually, there's two more things after this, so almost there. But the kernel must, as is rather obvious, I think, keep track of the I/O devices that are in use by which processes and their general state. And if we take a look at a diagram that's shown here, we can see that, like, in our process we have a file descriptor, and I said, all right, the file descriptor of this corresponds to, say, the socket that we have open. And they're just integers, and you can, I think, start to see why when we look at the diagram here, because really the integer is just the entry in the per process open file table that the operating system has on hand. And so we can see the socket that we opened, it has a number, if you just printed the integer, literally of 3. Why is it 3? Well, it's just, that's the array index in the per process open file table. With that said, the entry in there really just corresponds to a pointer into the system-wide open file table, and the system open file table is responsible for knowing things about whether that actually corresponds to a file, as in the sense of an inode, or whether it corresponds to some network stuff, and making sure that we are, when we want to read or write data, going to the correct location. So this gives you kind of some idea of what it's like, and in the system open file table, like, we'll have some pointers to the associated functions, read and write, IO control, close, whatever it is, and the same true for, say, network. There will be pointers to the appropriate read and write functions for the kind of device that it is. We'll also talk about IO scheduling, and as we talk about I/O scheduling, it's going to lead us into our next topic, but basically what I'm going to suggest is that when it comes to I/O, there might be good reasons to choose something other than just first come, first served every single time. First come, first served is certainly fair, and that is sometimes desirable, but it doesn't mean it's the most efficient. And when I say that, what I'm really talking about is something like, okay, you need to go to the grocery store, you need to go to the dry cleaners, you need to go to the bank, and based on where you're standing, the order in which you do those may be different. Because if the bank is 1 kilometer to the west of your current location, the grocery store is 3 kilometers west, and the dry cleaner is at the same location as the grocery store, it's fine if you go to the bank, then the dry cleaners, and the grocery store, but it's not sensible to go to the dry cleaners, then go to the bank, then go to the grocery store, because you have a bunch of unnecessary back and forth, right? While you're in the same plaza, you want to do the 2 chores that you need to do while you're there, otherwise you're just wasting time, right? It's not efficient. It's not as efficient as it could be. So the operating system will want to do something with I/O requests to try to make them as efficient as possible. And so this may require, like, rearranging some things. It might require doing them in a different order than had originally been foreseen. That's fine. As long as some request structure is maintained so that you have an idea of what requests are present, and when you intend eventually to do them, this is going to work. Thing about it, though, is like there has to be some limits, right? There are certainly chores that are not at all convenient to do, and there's always something closer by that you'd rather be doing, but you have to do certain things before too much time has elapsed to maintain at least like some basic level of fairness. Otherwise, it doesn't really work. And similarly, reorganization might take priority into account. If we're going to rearrange the order in which these things are, we might say, all right, well, we'll do the most important things first. And that's, again, within some limited bounds, just okay. Yeah. That's very important, actually, when we talk about hard drive operation, which is our next topic in the course. And so to wrap up this topic, I want to give kind of an overview of what happens when we are interested in, say, reading something from disk. If you think back to a much earlier topic where we talked about like doing a read in the sense of invoking a system call and all of that, we've actually like looked at it from the user space perspective, but now it's time to take a look from the other side and see what does the operating system have to do to actually open the file and see what happens. So if I want to open a file, right, the file system is going to associate a file named example.txt with some information about where on disk it is. We haven't talked about the file system, we haven't talked about inodes and stuff yet, but those exist. To read the file, then read commands will be issued such that the data ends up in memory, so I can do something with it in my text editor, right? And so if we look at this diagram, it actually gives kind of a nice overview of the I/O request lifecycle. I mean, it's a flowchart, it's a little bit hard to follow, but let's imagine, if you will, that the file is already open, just as we saw in our previous example where we were reading from user space, and we actually want to do a read. Okay, so in this diagram, like the flowchart in the middle shows like whose responsibility is what. So where it says user process, like then the boxes to the left and the right here are showing that this is part of the user process. Good. Now, so we have a request that results in a system call. And when the system call takes place, we're going to check and see if we already have what we need. If for some reason this data is already in memory, or if it was like network data and that data is already there, there's nothing we would have to do to go get it because we have it. Let's imagine that's not the case in our example. I mean, if we did, then we could just sort of return that information immediately and we don't have to do any of the other steps. Great. Congratulations, here you go. But if we can't send the data immediately, then we have to go to the next step. So we'll send the request to the device driver and we'll block the process that made the request if it's appropriate. If they asked for blocking behavior, then yes, we block the calling process. If they ask for non-blocking, that's fine. We will just carry on and say, yep, the event is in progress. So now we need to, in the device driver, take a look at the request, issue the commands to the controller, and tell the controller, presumably, to block until the data has been delivered. So when we do that, we are saying, all right, device, please do your thing. And we'll see then the device controller commands are issued such that our request is actually transmitted to the hardware device. When that happens, we will monitor the hardware device in the device driver and we'll take a look and see, has the operation been completed? And if the answer to that is yes, great, then we will generate an interrupt that says the data is ready so that others can do something with it. And the interrupt results in the interrupt handler running in the kernel and saying, all right, this device has sent an interrupt, which indicates that it's finished with whatever request you gave it. The job then of the interrupt handler is to store the data in a buffer if we were fetching data, so in this case yes, and signal to unblock the device driver. The device driver is responsible for figuring out which of the requests has completed, because there could be more than one, and indicate state change to the I/O subsystem, so device is available again, or request is complete, or queue size has decreased, whatever it is. And then we'll transfer the data to the process memory as per the request. We'll return from the system call, and then the I/O is complete, so the input data is available. When we did this with the read, from the system call point of view, we didn't really go into what the operating system is doing in the background, but I think we have a much better idea now, having talked about much more of sort of the internals and how it's supposed to work. That we now have to send it to the device driver. The device driver has to request the read from the hardware device. When the data comes in, generate an interrupt, and then transfer that data, deliver it to the requesting process. So it's a lot of steps, right? There's 10 distinct steps here, including like when the data has been transferred to the user process, we can mark it as ready to run again, such that when the scheduler chooses that process can be selected to run again and continue executing. So yeah, it's a complicated process, and there's a lot of work that has to be done to actually deliver the data, but yeah, from the perspective of the user, it's kind of transparent, right? Make your request, get blocked until it's ready, and then you continue executing when the data is there. In our next topic, we're going to talk about the disk scheduling, which I had mentioned previously. So let's leave it off here and continue there.